serotonin bound to the 2A receptor. It increases calcium levels, it increases protein kinase C. So what we're really looking at here is the 2A receptor mediated increase in calcium, which is actually leading to excitatory postsynaptic potentials. So it's kind of moved away from some of these metabotropic effects, even though it's a metabotropic receptor, but moving now to say this liberation of internal calcium can lead to excitatory postsynaptic potentials, and that can increase action potentials. Okay, so increase the output of those neurons where those 2A receptors are located. And then what does that do to this giant perceptual circuit? So LSD is basically now locked into that 2A receptor and causing constant excitatory postsynaptic potentials through this liberation of this cation, calcium. All right, so slowly and surely we'll get through this. Got 20 minutes. Okay, so a simplified schema of the thalamocortical circuitry, so the reticular thalamic nucleus. In particular, we're looking at the specific thalamocortical circuits. So you know that this is going to require drawing on my part. So first, let's just go over these circuits. So you have afferent sensory projections. Okay, so you have visual input, right? Your eyeball, your retina, has ganglion neurons that project back to the thalamus. So this first station here. And the thalamus, right, those thalamic inputs, they're can be called thalamic relay circuits. So they relay sensory inputs, and we're just going to focus on visual inputs. They relay visual inputs into the cortex, right? Pyramidal cells in layer V1, in primary visual cortex up here. Okay, so what then can happen, and this is where it gets pretty cool, is this side are the descending top-down processing projections. Okay, so it's called cortical fugal or cortical thalamic. So from the cortex to the thalamus. So cortical fugal is just another term for thalamus, but it's cortical thalamic input. So top-down. So from the cortex down to the thalamus, but it kind of, so this is now this we have to follow this dash dot, dash dot, dash dot, right, to the reticular thalamic nucleus. RTN. So this circle right here, the RTN, has serotonin 2A receptors on it, massive amounts. So serotonin release from those cortical fugal projections onto the reticular thalamic nucleus can bind to those 2A receptors. Those 2A receptors cause increased calcium concentrations and can increase the activity of these GABA inputs to the thalamic relay circuit and control them, really. Okay, so GABA control on those thalamic relay circuits. So this is top-down processing, right? So a sensory input coming in is that blue chair. Okay, so the blue chair comes up, thalamic relay circuits send that information up to the cortex, and the cortex says, here's that pattern of activity. There's the edges, right? There's the certain wavelengths of the inputs from the cones, and then that's all good and well. But there's also this, what usually does an object like that mean to me? What does that say? So that says, okay, that's probably, so through these cortical fugal circuits, you activate that reticular thalamic nucleus, and it can color or can alter what those inputs are doing. So it can say, well, that chair is usually in a certain, configuration. Like every day, well, every Tuesday and Thursday, I see that particular blue chair, so I expect it to look that way. So that's the top-down processing that happens. You have certain expectations about what the world looks like. And sometimes they're completely wrong, right? Like eyewitness testimony is exactly this, right? So you have particular afferent sensory inputs coming in through the thalamic relay circuits and saying, these are the sensory inputs that are coming in. And then you're in court as the eyewitness, and your brain, though, has already colored those inputs. You have this certain expectation. Oh, I was watching, Magnum PI the other night. Wow, that's an old show. Probably nobody even knows what that is. So I was watching this old show, about this guy who was robbing a store, and, I have this perceptual preconceived notion about what a perpetrator should look like. So that's activating these cortical fugal circuits, dumping GABA onto these thalamic relay circuits, and altering the sensory inputs to make it fit into my world. Okay, so that's the natural process, right? And that's all mediated by serotonin. Now the question is what happens if you take LSD and you just jam it into those 2A receptors and constantly activate or override or bypass these cortical fugal circuits and activate that reticular thalamic nucleus to put GABA onto these thalamic relay circuits and really mess up your inputs or produce a perceptual hallucination. Okay, so that's what we're going to look at. So those reticular thalamic nuclei. Okay, so what do those, so remember it's this one right here, the RTN. The thalamic relay circuits should be really straightforward, right? Thalamus relays information, afferent sensory information to primary visual, primary auditory, whatever. They're a generic class of cells, but they are important for relaying sensory inputs. But it's those reticular thalamic nuclei that are the top-down processing stations. So what do they do? Essentially, this is a nice characterization of those neurons, those reticular thalamic nuclei, is that they assist in organizing activity in the relay circuits according to characteristics of sensory input and attentional demands. Okay, so they help you to organize. This is exactly what top-down processing is. You have all these sensory inputs coming in, right? Every day it's like, oh, I'm just being bombarded. Can I pay attention to everything that's happening? Well, maybe, because again, your cortex has, already sort of things that you should be expecting in this life, right? You should expect the sky to be blue. So it is blue, right? Even if it's gray, right? You just have these expectations that it should be blue. So yeah, yesterday was a really nice blue sunny day. Actually, it wasn't. It was gray. But that's, so I have I have this misconception of what that day was because of sensory inputs, because of preconceived notions, because of top-down processing and attention. I wasn't even paying attention to the sky yesterday, right? So it's those reticular thalamic neurons that can grab hold of those relay circuits and say, this is what you should be looking at. This is what you should be focusing on. Okay, so again, this is this isn't really that important, but it's interesting, but it's not critical for your understanding of this, but it contains a topographical map of each sensory modality. That's the important part. So those reticular thalamic neurons, so I'm talking mostly about vision because we're talking about visual hallucinations, but it happens in the auditory world as well. And this actually has a lot to do with schizophrenia. Okay, so in schizophrenia, you have auditory hallucinations. With LSD, you have visual hallucinations. Aha, wait a second, how do those two things interact? Oh, maybe those hallucinations are through overactivity of serotonergic systems. But then what is the circuit that they're working on? Well, it's this reticular thalamic nucleus that can actually help participate in the ascending sensory information, as in the bottom-up inputs. Okay, so the thalamic relay nuclei. So now we go back to those relay nuclei, okay? We know that the reticular thalamic nucleus is helping to organize everything. But the relay circuits are really the important things that just simply are partly depolarized, respond to afferent stimulation with tonic firing of single action potentials. Okay, that's really hooray. That's retinal images, retinal activation going through ganglion neurons, going into the thalamus, and then sending these relay nuclei into this depolarized mode where they just convey that information. They relay those sensory inputs into the primary visual cortex. Right? Boring sensory topics. Okay, in tonic mode though, so tonic mode, that means they're depolarized. They fire in a manner that's related to afferent sensory input. Okay, so blue is blue, lines are straight up and down, right? Edges are perfect, like all those really basic sensory inputs that we learned about in 2200. And now it's because those thalamic relay circuits are, firing in perfect harmony. They're synced up with those sensory inputs. Like everything is great, beautiful. Okay, but they can go into burst firing mode. So now this is now where we have to try to think a little bit outside the box and think about that actually hyperpolarization does not mean shutting down. Hyperpolarization means that they are not in sync with sensory inputs. They're bursting. They have no clue what's going on. Okay, so in burst firing mode, sensory information is not transmitted effectively. So let's stop and think. So you have this, see if I can do it in a different way here. Okay, so your retina back here, right, has all the ganglion, all the photoreceptors, project back through the optic nerve. So our first way station of this, for this talk, are those relay neurons. So that's the thalamus. Okay, so those relay neurons simply, I mean, again, you know all the, I can't remember it even though I lecture on the visual system, but those pathways, right, that go into the thalamus and then simply back to V1. Okay, and so you have, you know, all the simple cortical neurons, all the complex, hypercomplex, right? All those things. You have colors back there. You have all this mishmash of information that's coming in. That's exactly what your retina is seeing, and then you have color. I remember this stuff. Okay, so that's all good and well. So when those relay circuits, when those relay neurons, if there's like, so let's say there's a, well, the blue chair we use as an example. So the blue chair, right, that's coming in, and those relay neurons, the visual input is coming into those relay neurons. These neurons are in a depolarized state, so they send off action potentials that represent the edges of that chair, that represent the color of that chair, all those basic properties that say there's an input coming in. Okay, but this isn't necessarily how the brain likes to work. So the brain also likes to have, so this is that, I think it's bottom up. I think there's probably a better word for this, but from the bottom to the up, to the top, to the cortex. But there's also top-down processing, which is much cooler. So top, down. Okay, so the top doesn't matter, but how we get to the down is what's really cool. So you have these, so I'm going to just make a small one and then I'll blow this circuit up. So you have right here the intermediate reticular thalamic neuron. Okay, so that little reticular thalamic neuron has GABA. And right, that previous slide just said that when these relay neurons are slightly hyperpolarized, so when this top-down processing is releasing GABA onto this relay neuron, you have this state of hyperpolarization. So now in the simplest, like in the easiest case, it's like if I were to leave this classroom and, you know, maybe I teach in a room that has red chairs all the time. So somebody might say, what is the color of that chair? Let's see, top down, all of a sudden my preconceived notions are turning in, and all of a sudden I get this burst firing of, it's a red chair, right? So it's kind of interfering, it's overlapping, overriding those sensory inputs. So information is not being transmitted effectively. So that blue chair now is becoming maybe just a red chair, or maybe it's a couch or something else, right? So that's an important concept to keep in mind, is that burst firing mode. Okay, so when there's that top-down input to the reticular thalamic nucleus is being activated, that's a GABA input onto that reticular thalamic neuron, that's a GABA input into that thalamic relay circuit that causes those relay circuits to burst fire and information is not transmitted effectively. Okay, so now you're hopefully starting to think that, aha, that's a hallucination, which it exactly is. Right, so in burst firing mode, that's what we have to really focus on. Those thalamic relay sensory neurons are hyperpolarized. Okay, which again is a bit like, just, do I dare say forget everything you've learned? No, I don't. But just now think about another way in which GABA can influence activity of your brain. Okay, so GABA can lead to this burst firing. So those neurons are still active, right? They're just not, even though you have this GABA inhibitory influence, they're still active. They're not completely shut down. Like that would be silly to shut these neurons down because then you wouldn't see, right? So you're just slightly hyperpolarizing them. You still have depolarizations and now hyperpolarizations. So information is being a bit messed up, right? There's a burst firing mode. So that burst firing is what's the red here. Because of these hyperpolarizations produced by activation of this reticular thalamic neuron, which is dumping GABA there, because of this top-down processing, these kind of preconceived notions. What you think the world should look like. Okay, and again, that's a natural process. That's okay. It's just when you override that system, when you take LSD, then it gets to be a bit of a dangerous, well, a hallucinogenic type of experience. So those thalamic relay circuits are hyperpolarized when that GABAergic projection from the thalamic reticular neuron is active. And how do they become active? So once again, this is another maybe principle of the brain that, we've seen this before with these descending projections on the pain pathways down to the spinal cord. Now we see that, those cortical fugal, those cortex to thalamic reticular neurons are also mediated by stimulation of serotonin, and in this case, the 2A receptors. Okay, so now I'm going to blow this up a little bit. Try to keep the same colors and just focus on so we have the thalamus, the relays, right, which project up to V1. I can do it. Thalamus, right, and then the reticular thalamic nucleus, RTN, which is GABA. So in a normal case, you have a depolarization, a couple inputs coming into this relay, telling you there's a blue chair, right? And now you can activate this descending projection, and lo and behold, these RTNs have 2A receptors, which when activated increase calcium. Calcium can have the ability to increase action potentials. And now GABA is released, causing some hyperpolarization in these relays. But when there's a hyperpolarization, there's all of a sudden these massive, out of sync bursts. Okay, and that's basically hallucination right there. I don't even think I have to go any further, right? So if you have LSD is sitting into that 2A receptor of that reticular thalamic neuron, overstimulating it, just constantly binding. It has a really strong affinity. So you have massive amounts of calcium inside that neuron, which will put the LSD stimulated release of GABA, right? So LSD causes lots of GABA to be dumped onto these relays. So now you have this state of constant hyperpolarization. But you also, so again, this is why, like, we go back to Hoffman's experience, right? He said that my surroundings transform themselves, right? It wasn't just this made-up world of dragons and whatever else. It was, let's say, this normal-looking chair that usually is coming in to those circuits. So you have the chair representation, but now all of a sudden, that chair is maybe melting or whatever. It's changing its patterns because of these hyperpolarizations and these burst firing, right? That's not transmitting information properly to V1. So now those edges, right, those crisp and clean edges that are usually coming in from the chair are looking like that. They're a different color. They're kind of floating around. They're doing whatever. Those simple cells, those complex cells are all just messed up. 5 minutes. Okay, so the reticular neurons become active. LSD binds to those receptors, those 2A receptors, overactivates those thalamic reticular neurons, which dump GABA onto the relay neurons, hyperpolarizes them. Sensory input is poorly transmitted, and right, I mean, it's basically like that's sensory inputs that are all you have coming through those relay circuits are edges and colors, right? That's basic sensory information. That's visual system stuff. So it's how do you mess up those inputs? You overstimulate those thalamic reticular thalamic inputs to those relay circuits, hyperpolarize them, cause burst firing, hallucination. Right? So this is, we go back to that original circuit, right? Serotonin 2A receptors on those reticular thalamic neurons, increasing calcium levels. There's enhanced GABA output. That enhanced GABA output throws some hyperpolarization onto these relay circuits. But again, it's important to keep in mind that they still have those afferent sensory projections coming in. There's still depolarization. So there's all this, they're just flooded. They're flooded with hyperpolarizations from one side, and they're flooded with depolarizations on the other side. And now there's all this burst firing that's happening. So information is not being transmitted effectively. So you've really messed up this circuit. You've hijacked this normal top-down processing, these cortical-fugal circuits. You've overstimulated those, and now you've really produced just basically a hallucination, just like that. Okay, so this is in the visual world that we're really focusing on here. So LSD binding to the 2A receptors in the reticular thalamic nucleus activates that GABA projection. Hyperpolarizes those relay neurons, generating rhythmic bursts of action potentials in the relay. Loss of sensory specific firing. Okay, so it's this increased spontaneous background activity that your brain just has to try to figure out, what does that mean? I don't know what that is. Have I ever seen this before? Maybe. So it kind of interprets its own inputs. So what you lose is this impairment of signal to noise ratio of thalamic relay transmission. So that's why I think that's important to keep in mind, right, that it's this signal to noise. There's usually blue, blue, signal, signal, signal. Now all of a sudden, I mean, it's not melting out here, right? It's melting in here. There's this signal, there's this loud noise, all this noise overcoming that signal, and it's causing this interpretation by your brain, right? So the chair, to everybody else, the chair is still a chair. So I shouldn't even draw it as a melting chair. But to you, it's a melting chair, right? It's a blue chair that looks like it's going, it's bleeding or whatever.